starting with the Euler momentum equation for vorticity and our definition of vorticity, let's now make some simplifying assumptions that are representative of many physical systems. We're going to consider two simplifying assumptions that make this equation a little easier to interpret. So first of all, we're going to assume that we have a conservative force. So our first assumption, one, let our force F be conservative. As an example of a conservative force, gravity is a conservative force. And a special thing about conservative forces is that the force itself, the vector force, can be represented as the gradient of a scalar potential. So if F is a conservative force, then it can be represented as minus the gradient of some potential phi. So here's our potential, and here's our force. Our classic ones are gravity, electrostatic forces, spring forces, many of the forces that we interact with in sort of basic physics. Now, by vector identity, if F is given by grad of phi, then we have that the curl of F must be 0. So for any conservative force F, then its curl will be 0. So that term vanishes from our equation set by vector identity. Doesn't matter what the scalar potential is, how it varies in space or anything like that. And this is true for any fluid, compressible or incompressible. Now, our second simplifying assumption is going to help us get rid of another term in the vorticity equation. So for our second simplifying assumption, we're going to assume that our fluid is what is called a barotropic fluid. Assume a barotropic fluid. In a barotropic fluid, the density is given by a simple equation of state which only depends on the pressure. Conversely, the pressure is given by a simple equation of state that only depends on the density. Critically, there is not an independent temperature dependence, for example. So rho is not a function of P and T. It's a function of P only. And likewise for P if we turn it around. As an example of this, the polytropic equation of state, even though we phrase the polytropic equation of state as one related to temperature, right? We said that rho is proportional to T to some m, but for an ideal gas, we also said that P is proportional to T to some m plus 1. Well, what that means is that a polytropic equation of state is actually also a barotropic equation of state, because under the system, let's consider, for example, the pressure. The pressure can be written as the density raised to the 1 plus 1 over m, and there's a corresponding inverted relationship to write the density in terms of the pressure. So barotropic equations of state come up quite frequently. A real limit of this is that density is a function of pressure that's a constant, right? So incompressible is a limit of barotropic. So if rho equals rho of P equals a constant, that also, in some senses, that's a limiting version of a barotropic system. So the simplification that we're about to show holds there too. You'll see that simplification we hold are about to show holds in that case even more obviously. So if we make this assumption, if rho is barotropic, is a function of p alone, then grad rho can be written as the partial d rho dp, this is some thermodynamic quality of our system, times the gradient of pressure. We can do basically a change of variables from density to pressure, since density is only a function of pressure. That's the power that a barotropic system brings. Under this simplifying condition, our term grad rho cross grad p that shows up in the baroclinic forces, well, that is d rho dp times the grad of p crossed with the grad of p. And as we know from vector identities, this must be 0 because the cross product between two vectors, it must be perpendicular to both of them, and there's no cross product between two vectors that are the same vector or that are parallel to each other. So if we have a barotropic equation of state, then the term 1 over rho squared, grad rho cross grad p, is also 0, and there is no baroclinic forcing, no baroclinicity if barotropic. All right. So under these two assumptions, right, so to recap them here, one, f is given by the curl of some scalar, so it's a conservative term. Two, the density is barotropic, it's some function of, say, pressure alone. Then our vorticity equation takes a drastically simplified form. And in particular, it takes the form d by dt of vorticity equals del cross u cross omega. This is still fully nonlinear. This also is fully compressible. This permits compressible motions. We haven't assumed incompressibility, but this vastly simplified equation for vorticity will be extremely handy when considering the evolution of vorticity and making analogs to other similar vector quantities.